Here's the second part of this video where I'm going to show you how to solve these equations in Matlab. And I'm probably not going to spend a ton of time on this because you'll quickly see that this is basically the same code I've been using for the other problems I've shown you in Matlab as far as solving ODEs. And so really I'm using the same code, and I'm just going in and putting in whatever's representative of the problem I'm solving. So basically I might change the number of equations, the variables, the rates. In this case we had a lot going on with the rate laws, and then the differential equations. So just as a quick reminder, this is a summary of the equations we derived for example 6-6, and so these were the mole balances, and then we had the rate laws, and these were the rate laws that were given, and then these are the ones that we derived, and then these were the total, or the rate net for the rate laws. So, and then we needed concentration for the concentrations that appear in these rate laws, so we have this here. And you could get a concentration for any of the reactant or any of the species in this, so you would just write another rate equation for, like, say you wanted the concentration of H2O, so then it would just be CH2O equals CT naught multiplied by FH2O divided by FT. So I just have these because these are the ones we needed. And then we have the constants, and this is the reactions. So moving over to the code, the first thing you need to do is write a function that solves the right-hand side. So this time I called it example 6.6 function. And so just remember that whatever you call this, it needs to be named the same. So example 6.6 function.m. And so in this I'm solving 6 ODEs. So I need this df/dv to be an array with 6 spots. And so this is really a column. Well, so this is 6 rows in 1 column. And then this is how I set this up. So the first one, so F1. So F1 was equal to F and H3. And I just realized that the way I define this, these are actually all capital. So I have the first one, F1 is FNH3, F2 is FNO, F3 is FN2, F4 is FH2O, F5 is FO2, and F6 is FNO2. And if you remember, the reason why you have to do it like this is because you're only allowed to have one name for the dependent variable, and so you just have to create an array if you have more than one equation. And so then I have the constants. So that was these. So, and these were given in the problem. So CT naught is equal to 0.2, K1NO is 0.43, K2N2 is 2.7, and K3O2 is 5.8. Now I have this FT, which was, so that's the sum of all of the molar flow rates, so F1, F2, F3, F4, F5, F6. And then I have the concentrations, so CNO is equal to CT naught multiplied by F2, and that F2 is, the way I have it defined, is FNO, so this is FNO divided by FT. CN2 equals CT naught multiplied by F3, and so if you remember, if you look up here, I have F3 defined as FN2 divided by FT, and CNH3 is multiplied by CT naught, or is equal to CT naught multiplied by FNH3 divided by FT, and CO2 is equal to CT naught multiplied by F5, which is O2, FO2, divided by FT. And then I just put in all the definitions for my rate loss. So first I put in the ones that were known. So the R1NO is equal to this. R2N2 is equal to this. And R3O2 was equal to this. And those were given. And then I have all of these that we derived previously on the board. So R1NH3 was equal to 2/3 R1NO. R1N2 was equal to -5/6 R1NO, and so on. And then, so these are the individual portions that we derived from the stoichiometry, and then these were the sums. So some people call these nets, so that would be like RNH3 net, RNO net, but I'm just calling them RNH3, RNO, etc. So then I just put these in that we derived. So we know that we found that RNH3 was equal to R1NH3, RNO was equal to R1NO plus R2NO, and so on. And then finally, we have the differential equations that we're solving. So right there. So df dv1 is equal to RNH3. df dv2 is equal to RNO. df dv3 is equal to Rn2, and so on. So, and at this point, I'll often go through and make sure all my signs look right, like I talked about previously. But since I already did that on the board, I'm not going to do it here. So then once you have this, so this is just calculating the right-hand side of this equation, then you can go to, then you need to write a script, and as you can see, this is basically the same script I've been using all along. I just changed a few things for this problem. So I'm using ODE 45, which is a Runge-Kutta solver. Could probably also use ODE 21, but I always start with ODE 45. And then you give it basically your right-hand side. And then, so with this problem, so you always need to give it for your independent variable, you always have to give it the beginning and end, so basically the volume. So we know that it starts out at 0, and then we need to tell it what the volume is, so the final volume. And this problem didn't actually give a final volume, so I kind of played around with that a little bit, but you have to put something in. So normally the way you would, if you don't know what that is, normally you would just put something in. And then if you don't get the conversion you expected, then you would try something else. And then these are the initial values for the flow rates. And also the problem didn't give any values for these, so I just put some stuff in. And so I don't know, so when I run this, I'm actually getting a really low conversion for NH3, which I don't know if that's right. And so I'm probably putting in, I could probably play around with these values some more and with the volume and get a better conversion, but since the whole point of this is to just show you how to run this in Matlab, I'm not going to worry about that. So this is what I put in for the initial values, and then I wanted to also show you how you would calculate the selectivity in Matlab. This is for the output, so this would be the overall. So if you remember, there was a definition for instantaneous selectivity, which was the rates divided by each other for what you're interested in. And there was also the overall selectivity, which was the exit molar flow rate of the desired product over the exit molar flow rate of the undesired product. So calculating it this way, I could have just taken the last value that I got for the flow rates and divided them, but I ended up just dividing everything, and then I'm just looking at the last number in the array it gives me. And then I also wanted to calculate the conversion of NH3, and the reason why I did that is because I was playing around with these numbers trying to improve the conversion, but I gave up pretty fast. So anyway, the way I did that is I have basically NH3 naught multiplied by, well, F NH3 naught minus F NH3 divided by F NH3 naught. And so I just put in a value for this, so that should be whatever I'm putting here. So that's the initial amount of NH3, and then this is the flow that it's getting back for NH3, and so then I can calculate, I can see what the conversion looks like as I go down the reactor doing it this way. And then I'm just plotting everything, so plot, and then I have V, and then if you remember, you get, since I'm solving 6 equations, I get back an array, so I'll just run it real quick. And I'm going to run it again and look at the plot closer, but I just want to show you this. So if you remember, so I'm getting back V, which I put in 0 to 100, so this is 0 to 100. And then if I just look at F, then you'll see that I have 6 columns, and it's because I have, so it's because I'm solving 6 equations. So the first one, the first column is the solution for the first equation, the second one is the solution for the second equation, so this would be NH3, this one is NO, N2, and so on. So that's why when I plot this, I have volume versus F, and then this says every row in the first column, so that would be NH3. And then you just do that for all of these. And so I have X label, Y label, and then I put a legend in this time because since I'm plotting so many things, it got kind of confusing looking at it. So that's how you do a legend. So you can either you can type a command like this to get your legend, or when you get your plot. So I'll actually run this now. So then when you get your plot, and this is putting these numbers in kind of funny, so I would probably go in and edit this, but I'm not going to worry about, well, maybe I will. So so this is the plot you get, and you can already see that the conversion for NH3 is really low, but just eyeballing some of this other stuff, I think, I mean, since I haven't seen a solution for this and it didn't give the initial concentrations or final volume, I'm not really sure how this is supposed to look, but just eyeballing it, I would expect O2 and N2 to increase because they're forming in reaction 1 and 2, and then I would expect them to drop off because they're being used up in reaction 3. So if I look at, say, O2, which is this pink line, you can see that it increases and then it drops off. And then also N2 does the same thing. It increases and then it drops off. And then for NO, NO is being used up in reaction 1 and 2, and it's not being formed anywhere else. So you would expect that to drop off. You can see that that happens. And now I'm kind of wondering if that's why the conversion for NH3 is so low. I probably need to add more NO initially than I am. So I might try and mess around with that. So, but just eyeballing it, you can see that things are kind of doing what they probably should do. So then you can determine that's probably right. And so to mess with some of these fonts, I'm not going to spend a lot of time on this because I already did in a previous video, but just to kind of remind you how to do all this, you would go to Tools, Edit Plot, and then you can click on it. And then that, so I double clicked on it, and then that opens up this thing called Plot Tools. And so then you can just kind of mess with everything in here. I really like to get in here and just change things so they look good. This is one thing I really like about Matlab, is you can make your plots look really good and professional. So so it kind of bugs me how these came out, so I want to just show you how, like if I was editing this plot for, I don't know, like a paper or even an assignment, I mean, you just want your stuff to look nice. And so I would, first of all, rewrite these. So I want to use LaTeX because I think it looks good. So I can re-edit these. And so you can also do this from your script. Like you can write a script that will do all this for you. Okay, so then I go, and you can see that these already sort of look like the subscript I want, but I think it looks, I actually like it better using LaTeX. So what you would do is, once you get these entered like this, and you know that you have legend selected, go to More Properties, and then look for the interpreter. Right now it's on text, so I want to change that to LaTeX. And then you can see what they look like now. Like I just think they look a lot nicer. So you don't have to do this, but I just want to show you that it's possible to do. And then going back to the plot, so on the x-axis, I'm pretty happy with the spacing. I want to mess with this. So I want this font to look the same as these. So I'm going to change this to LaTeX and make this like 14. And just need to add these. And then I want to mess with the y-axis. So if I go back, well, first I guess I can mess with the font a little bit. So change that to LaTeX. And then I have kind of the same thing as the legend, so F NH3. So then you can see that looks pretty nice now. I'm going to make it bigger though, so 14. So FNH3, FNO, FN2, FH2O, FO2, and FNO2. And then going back to the actual plot, so I have, and I guess I could have entered this here too. So you can either double click on it and edit it, or you can edit it from here. And so I haven't put a title in yet, so for the title, I'm just going to say example 6-6. Double click on this, change that to LaTeX. And then just to show you, you can also change the ticks on this, because I'm kind of noticing that the y-axis looks, I mean, it actually looks okay, but I'm going to show you how you can change the ticks. So let's just say I want to step by, well, actually I could just delete some, like I'll just say step by, right now it's stepping by 0.01, so I'll just say 0.02. And then I can say apply. So yeah, then you can see it removed some of the ticks, but the 0.01 was probably actually better. I just want to show you that you can do that. So apply. So anyway, and then you can just save this. So getting out of that. And all of that stuff I just did on the plot, you can write code to do that. I just usually do it on the plot the way I showed you with the plot editor. But if I was doing a lot of plots, I would probably figure out how to do it in here better. So anyway, that's how you set up and solve example 6.